Welcome everyone. Imagine you are a detective looking for a hidden treasure in a massive, infinite desert. In the world of ordinary real numbers, sometimes you follow a mathematical treasure map only to find that the treasure simply does not exist. But today, we are entering the complex number plane. It is a magical, complete world where no treasure map is ever a dead end. We are going to explore the fundamental theorem of algebra, which is the ultimate guarantee for mathematical detectives. Now that we know we are hunting for mathematical treasure, let us define what our map looks like. In formal terms, the fundamental theorem of algebra states that every non-constant polynomial equation with complex coefficients has at least one complex root. A polynomial is simply an expression made of a variable raised to positive whole number powers multiplied by constants. The highest power is called its degree. Because this theorem guarantees at least one root, we can keep factoring the polynomial, which leads to a powerful conclusion. A polynomial of degree n will actually have exactly n roots in the complex plane. This brings us to the mathematical form of our treasure map. Here is the general equation for a polynomial, which we call p of z. The variable z is a complex variable, meaning it can take on any value in the complex plane. The values an through a0 are complex constants called coefficients. For this polynomial to truly have a degree of n, the leading coefficient an cannot be 0. If we change these coefficients, the shape of our polynomial changes. But the theorem guarantees that no matter what valid coefficients we choose, this equation will equal 0 somewhere. Before we prove why this theorem works, let us see it in action with a classic problem that breaks in the real number system. We are given the polynomial equation z squared plus 1 equals 0. Our goal is to find the roots. First, we isolate the variable by subtracting 1 from both sides, giving us z squared equals negative 1. Next, we take the square root of both sides. In the real number system, taking the square root of a negative number is impossible, and we would be stuck. Continuing from our previous step, we bypass the real number restriction by using the complex number system. We introduce the imaginary unit j, which is defined such that j squared equals negative 1. By substituting this unit into our equation, we find our answers. We get a positive and a negative version because squaring a negative also yields a positive result. Our final roots are z equals j and z equals negative j. The theorem promised at least one root for this degree 2 polynomial, and we found exactly 2. Let us look at what we just solved visually. This diagram shows the magnitude of a polynomial forming a three-dimensional bowl shape. If you only look along the flat real axis going left to right, the bowl never dips down to 0. Its lowest point is at a height of 1. This is why real number math says there is no solution. But when we expand our view to the entire complex plane, we can clearly see the bowl dipping down to touch the floor exactly twice. These red dots are the roots we just found at the imaginary numbers j and negative j. Now let us tackle a slightly harder problem, finding the cube roots of unity. We are given the cubic polynomial z cubed minus 1 equals 0. Since the highest power is 3, the theorem guarantees exactly 3 roots in total. We start by factoring the polynomial into a linear part and a quadratic part, using the standard algebraic formula for the difference of two cubes. For the whole expression to equal 0, either the first piece is 0 or the second piece is 0. Solving the first piece gives us our first root, z equals 1, which is a purely real number. Continuing with our cubic equation, we must now solve the remaining quadratic piece, z squared plus z plus 1 equals 0. We use the standard quadratic formula, which is a reliable tool for finding roots of any degree 2 polynomial. We carefully plug in our coefficients where a, b, and c are all equal to 1. After substituting the numbers, we simplify the terms inside the square root. This leaves us with -1 plus or minus the square root of -3, all divided by 2. In our final steps for this example, we deal with the square root of a negative number. Just like before, we replace the square root of -3 with the imaginary unit j, multiplied by the square root of 3. By splitting the fraction, we successfully find the other two roots. Altogether, our degree 3 polynomial yielded exactly 3 roots in the complex plane, 1 real root and 2 complex roots. We have completely solved the system without any dead ends, exactly as the theorem promised. Now that we have seen the theorem perfectly predict the number of roots, let us understand why it is true. We will prove it using a brilliant strategy called proof by contradiction. We will assume the exact opposite of our theorem is true and then show that this assumption leads to an impossible, ridiculous conclusion. To do this, we will rely on Liouville's theorem. This theorem states that if a function is entire, meaning smooth and differentiable everywhere, and bounded, meaning it never grows infinitely large, then it must be a perfectly flat, boring constant function. Let us begin our proof by setting up the contradiction. We start with a general polynomial p of z with a degree of at least 1. We pretend that this polynomial has absolutely no roots anywhere in the complex plane. This means p of z is never equal to 0, no matter what complex number we plug in. Because it is never 0, we can safely create a brand new function, f of z, by taking the reciprocal of p of z without ever worrying about dividing by 0. Because polynomials are smooth everywhere, our new function f of z is also smooth and continuous everywhere, making it an entire function. Continuing our proof, let us think about what happens when we travel very far away from the origin. As the magnitude of z becomes incredibly large, the highest power term completely dominates, and the value of the polynomial explodes toward infinity. But remember our reciprocal function f of z? If the bottom of a fraction grows infinitely large, the overall fraction shrinks towards 0. This means that far away from the origin, our function f of z is practically 0. Because it shrinks to 0 far away and never divides by 0 anywhere else, it can never grow infinitely large. It is trapped. It is a bounded function. This brings us to the final result of our proof. The trap has sprung shut. We have a function f of z that is both entire and bounded. According to Liouville's theorem, the only way a function can be both entire and bounded is if it is a constant. But if f of z is a constant, then its reciprocal, our original polynomial p of z, must also be a constant. This completely contradicts our very first rule, which was that p of z is a non-constant polynomial. Because our assumption led to a mathematical impossibility, p of z must equal 0 somewhere. The theorem is proven. So we have proven that the theorem holds, but why does this matter in the real world? The fundamental theorem of algebra is the bedrock of modern engineering and physics. In electrical engineering, when designing filters or analyzing control systems, engineers use polynomials to model how a system responds to different frequencies. The roots of these polynomials, called poles and zeros, tell the engineer exactly whether a system will be stable or whether it will vibrate out of control. If the complex plane did not guarantee these roots existed, engineers would have blind spots where they could not predict a machine's behavior. Let us summarize the most important ideas we have covered today. First, the fundamental theorem of algebra assures us that no polynomial equation is unsolvable. As long as the equation has a degree of at least 1, it is guaranteed to have at least one root in the complex plane. By repeatedly applying this fact, we know that a polynomial of degree n has exactly n complex roots. This beautiful truth transforms the complex plane into a perfect, complete arena where every mathematical question of this type has a definitive answer. You now have the ultimate tool for solving polynomials.